The Earth System, a video series for educational institutions for free use presented by the German Geological Society, the DGGV. Hello everyone, I welcome the viewers of another episode of my video series on the Earth System. As with all other videos, I would like to point out the opportunity giving me feedback if you have any questions or comment. You will find my email address on the first page of this video or on the website. After discussing the evolution of the oceanic crust in comparison to the lithospheric mantle and the evolution of the oceanic lithosphere over time in the last video, I would now like to focus on the oceanic crust, that is the part of the oceanic lithosphere that is completely formed at the spreading zone of a mid-oceanic ridge. Here we see the illustration that I already showed in one of the previous videos of the formation of the oceanic lithosphere. The main focus was on the structure of the oceanic lithosphere as a whole and how its thickening and increase in average density can be explained. In this video, as I said, I would now like to concentrate on the oceanic crust in the area of the spreading zone, and there I will start with the melt formation, which begins up here in the asthenosphere directly below the spreading center. I would first like to discuss how the melt actually develops, which accumulates in the magma chamber and from which the oceanic crust is formed. The melt is an extract from the uppermost asthenosphere. It has been melted out of the asthenosphere, but only certain parts go into the melt. Other parts remain solid. This then creates a melt that has a different composition than the mantle rock from which it comes. This is because some minerals prefer to melt under the pressure and temperature conditions at the top of the asthenosphere, while others remain solid and do not melt. What remains, I mean the solid part, then forms the lithospheric mantle directly below the spreading center and therefore directly below the moho. This is the boundary between crust and mantle, which is called the Mohorovičić discontinuity after the Serbian geophysicist Andrija Mohorovičić. It is actually called in its short form moho. Mantle rocks belong to the group of peridotites, which are the rocks that consist primarily of two minerals, olivine and pyroxene. Then there is a little bit of plagioclase, which is a mineral that belongs to the group of feldspars, which are actually more typical of the continental crust. However, we have to consider that plagioclase is only stable in the upper regions of the asthenosphere. Deeper down, it is replaced by spinel. There are, of course, a few other minerals that occur here, but in order to understand what happens during the melt formation, the ones I just mentioned and which are also mentioned here in this figure are sufficient. Pyroxene comes in two variants, diopside, which is a clinopyroxene, and enstatite, which is an orthopyroxene. They differ in their crystal form. Diopside is monoclinic, hence clinopyroxene, and enstatite is orthorhombic, hence orthopyroxene. But I won't go into these differences any further here. What is particularly important is that the two pyroxenes have different melting temperatures. Therefore, the diopside is already melted while the enstatite still remains solid. And this is of course very important for the composition of the resulting magma. These minerals, diopside, enstatite, olivine and spinel or plagioclase, form the rocks that belong to the peridotite group. There is the leusolite, named after a village in the Pyrenees where this rock occurs. The harzburgite, named after Bad Harzburg at the Harz Mountains in Germany, and the dunite, which is named after a New Zealand mountain where this rock occurs. It is a very common practice to name the rocks after the places where they were first described, as in these cases. Well, in the figure, we see that these three rocks, leusolite, harzburgite and dunite, each contain different amounts of the minerals. However, the differences have to do with the formation of the basaltic melt in the spreading zone. The original composition of the mantle rock at greater depths corresponds to a leucite. This rock is normally expected to be at the bottom of the already thick and mature lithosphere at a depth of 70 kilometers or so. In the partial melt beneath the spreading zone, it is primarily diopside and plagioclase from the leucite that are melted, while anstatite remains solid. This means that the solid portion of the rising asthenosphere below the spreading becomes depleted in diopside, and as one component is removed, becomes increasingly enriched in anstatite. When the asthenosphere becomes solid toward the side, hasbogite is formed. This is the case here in the upper layers of the lithospheric mantle, always near the spreading center. At very high degrees of melting, nests can sometimes form that consist almost exclusively of olivine. This rock is then called dunite. It consists of over 95% olivine. Now let's have a look at the magma chamber directly beneath the spreading zone. For this I have a figure with a close-up of this section up here. The basaltic melt rises into a magma chamber in the spreading zone. This melt contains mainly diopside and plagioclase and in varying proportions, but comparatively little, olivine. And this means that the basaltic melt has a completely different composition than a mantle rock, which is essentially due to the different melting behavior of the individual minerals. Okay, so much for melt formation. In this figure, we see a schematic representation of the magma chamber in the spreading zone at the mid-oceanic ridge. That is the zone that again and again is opening up so that magma can flow into it from below. And here, the oceanic crust with its various layers is formed. Essentially, there are three layers. The top is characterized by submarine basalts, which usually occur as pillar basalts. Below these are the so-called sheeted-dike structures, which is entirely composed of dikes through which magma rises up to reach the seafloor and extruding as lava. When the magma flow stops, the lava in the dikes also cools. The rock formed in the dikes is called dolerite. It is something in between the basalts on the seafloor, which contain a lot of volcanic glass, and the gabbros further down, which are completely crystallized. The lithospheric plates are continually moving apart from each other, and when a new fissure opens, the same dike that has just cooled down can split open again, and another dike brings lava to the surface of the seafloor again. This is a process that repeats itself over and over again after days, months, or years, just as long as the spreading in an ocean continues, and during this process, the sheeted-dike-complexes, which look like a sheeted series of rocks, form in the middle part of the oceanic crust. This is the second layer of the oceanic crust. The third and thickest layer consists of gabbro. This rock has the same chemical and mineralogical composition as dolerite and basalt, except that the gabbro is completely crystallized and coarse-grained rock, while basalt contains mostly glass. Due to the very fast cooling in the seawater, there was no time for crystals to grow. Only those that were already floating in the melt can be recognized as crystals in the basalt. The fine-grained dolerite sometimes also contains glass, but it is already mostly crystallized, however, with very small crystals. I go through the three layers again in detail. First, the pillar basalt, that is the topmost layer. This is a photo that we took with the diving robot at a spreading center in the southern Atlantic at a water depth of 2,500 meters during the Polarstern expedition PS 119, which I was part of. You can see the rounded structures that were created when molten lava comes into contact with the cold water on the seafloor as it flows out and is then rapidly cooled into such spherical structures. These spherical structures are called pillows or pillow lavas. Each individual pillow is approximately 1 meter in diameter. This schematic representation shows how it works. The lava is pressed upwards from a dike, and the spherical shapes form in the water directly at the outflow location. When more lava pushes from below, the pillows that have just been created burst open and the lava flows out again, creating more pillows. This continues until the supply of molten lava ceases, and the result are these rounded formations, the pillow lavas. Such pillow lavas often are found fossilized. These are some deposits of oceanic crust and lithospheric mantle that are literally scraped off of the oceanic crust when it is being subducted. And later, this material is integrated into the orogenetic processes of mountain formation. Such off-scraped oceanic lithosphere is then called an ophiolite. I will explain these ophiolites in more detail in a later video. In any case, we can find such pillow structures representing the fossil seafloor in such ophiolites. This photo shows a very nice example of pillow basalts from the Wadi al-Jizi in Oman, where the most beautiful and largest ophiolite in the world is exposed. The pillows shown here formed about 85 million years ago at a spreading center of the Neotethys Ocean, which has now largely disappeared because it was almost completely subducted. The next layer is the sheeted-dike-complex. They are named this way because they look like layers which we know from sediments. But it's not stratification in that sense. They are dikes, that is the fissure in which the liquid lava rises from the magma chamber to the surface to flow out there. At some point, the lava stops and cools within the dike. The cooling occurs very quickly at the edges, creating a thin, chilled margin made up of volcanic glass. It often happens that a dike penetrates into an existing dike that has just been formed a short time before. This older dike is split into two halves, which then are referred to as half-dikes. You can recognize them by the fact that, in contrast to the complete dike, they contain only one chilled margin on one side. That is shown here in this schematic view in the middle of the figure. The lower part of the oceanic crust is composed of gabbro. Gabbro has the same composition as basalt or dolerite, except that larger crystals grow here. The individual crystals are a few millimeters to centimeters in size, and there is no volcanic glass in the gabbro because this rock had enough time to crystallize. Volcanic glass is always a sign of particularly rapid cooling. This is what gabbros look like. The black minerals are pyroxene and the light ones are plagioclase. You can't see it in the photo, but you will also find a small amount of olivine in the rock. Sometimes the gabbros also show layers, that is, the layered gabbro. However, it should not be confused with the sheeted-dike-complex. This layering is due to cooling effects in the lower part of the magma chamber. At the boundary between lithospheric mantle and gabbro of the oceanic crust, there can be alternating layers of mantle rocks, for instance peridotites and gabbros, which can have very irregular shapes in a zone of hundreds of meters, as can be seen here. The brownish rock is peridotite, the lighter layers consist of gabbro, and you can see here that it is a quite complicated interfingering of the two rock types here along this exposed fossil moho in the Wadi al-Jizi in Oman. Okay, we have now taken a look at the structures of the oceanic crust. In the next video, I will discuss the convection currents in the mantle and beneath the spreading zone and how melt formation is related to these convection currents. This time, thank you for listening, and I'll be happy if you stick around. And I recommend continuing with the video on convection currents in the Earth's mantle.